Welcome back. In the following videos I will discuss the concept of maximum power point tracking, or as commonly called MPPT. This concept is very unique to the field of PV systems, and this is also brings about a very special application of power electronics in the field of photovoltaics. The concepts discussed in this blog are equally valid for cells, modules and arrays, although maximum power point tracking MPPT concepts are usually employed at PV module array level in practice. The learning objectives are first to understand the need for a maximum power point tracker in a photovoltaic system, and secondly to familiarize with some common or simple direct and indirect maximum power point tracking techniques. As discussed many times in this MOOC, the solar cell has an IV curve as shown in the figure. As a quick recap, you might remember how the IV curve of a PV module is similar to that of a single solar cell, as the PV module is merely an interconnection of several solar cells. A series or a parallel interconnection of cells increases the voltage or current respectively, but the overall nature of the IV curve remains the same. In a similar manner, it can be said that the interconnection of PV modules to form a PV array would yield comparable IV curves, albeit at different IV levels. Thus it is reasonable to consider the IV curve of a solar module or array similar in nature to that of a solar cell. So let's head to the simple IV curve of a solar module. Now the IV curve is nothing but the current voltage curve. This IV curve of a PV module is defined for a unique set of temperature and irradiance conditions. For instance, if the irradiance or illumination were to increase, the IV curve would also change to a higher level. In general, a higher irradiance gives a better IV curve, but a higher temperature gives a worse IV curve, and vice versa. Now let's try to understand the concept of the operating point. At a given point in time, the solar module operates at a particular voltage and current. The point of the IV curve where the solar module operates is called the operating point. For a given irradiance and temperature, an operating point on the IV curve corresponds to a unique IV value. We know that power is equal to voltage times current. If we draw the power voltage curve or the PV curve, it takes a form as shown. Of course, an operating point on the IV curve will also correspond to a unique operating point on the PV curve. Now, what is the significance of the P on the PV curve of a solar module? Well, this is the power that is produced and delivered to the rest of the PV system and eventually the load. Therefore, it's clearly advantageous that the solar module operates at maximum power as seen in this figure as the peak of the PV curve. Now, without any external electrical manipulation, the PV module's operating point is largely dictated by the electrical load seen by the PV module at its output. To get maximum power delivered by the PV module, it is therefore imperative to force the module to operate at the operating point corresponding to the maximum power, or as it's generally called, the maximum power point, MPP. This point corresponds to the peak of the PV curve, or the knee of the IV curve. The simplest way to do this is to force the voltage of the PV module to be that at the maximum power point, called VMPP, or regulate the current to the right amount as that at MPP, called IMPP, using converters. But what if, after forcing the PV module to operate at maximum power point, the ambient conditions, like irradiance or temperature, change and in turn cause the IV or PV curve to change as well? This would mean that the old maximum power point is no longer valid under these conditions. Thus, to be continuously at the maximum power point at all times, we would need to track any such changes in the IV curve and find out the new maximum power point. This process is called maximum power point tracking, or MPPT, and the devices that perform this process are called maximum power point trackers. So, how do these maximum power point tracker devices work? A maximum power point tracker device is nothing but a hardware implementation of a maximum power point tracking algorithm or algorithms. There are several algorithms to track the maximum power point effectively. These are also called maximum power point tracking techniques. Some of the modern literature talks about two broad categories of maximum power point tracking techniques. Indirect maximum power point tracking, like fractional open circuit voltage method or the fixed voltage method. Direct maximum power point tracking, like the perturb and observe methods or the incremental conductance methods. Each of these techniques have their own advantages and disadvantages. Let's talk about indirect maximum power point tracking first. Let's consider the indirect maximum power point tracking. In this kind of tracking, simple assumptions and periodic estimations of the maximum power point are made with easy measurements. An example from practice is the fixed voltage method. This technique is based on adjusting the operating voltage of the solar module only on a seasonal basis. This is under the assumption that higher maximum power point voltages are expected during winter and lower maximum power point voltages are expected in summer, from the same level of irradiance. Of course, this method is not very accurate, and accuracy is increased if such an idea is implemented in a place with minimal irradiance fluctuations on a particular day. One of the most common maximum power point tracking techniques in indirect tracking category is the fractional open circuit voltage method. This method exploits the fact that a good approximation of VMPP is given by constant K multiplied by the open circuit voltage VOC. This constant K for crystalline silicon is usually found to be around 0.7, 0.8 in practice. In general, constant K is based on the PV technology and the kind of solar cells in use. How is this technique rationalized? Let's discuss that for a moment. We know that every illumination level and therefore irradiance level corresponds to a particular IV curve and therefore a specific level of the VOC, the open circuit voltage. It is found from practice that for a range of IV curves, the ratio of the VMPP to VOC shows little variation. Thus, for changes in irradiance, if the VOC can be measured quickly, the VMPP can be easily estimated as a fraction of the VOC, the open circuit voltage. This technique is easier to implement compared to some of the more complicated techniques. What then are the drawbacks of this technique? Well, first, as the concept of K is just an approximation, this method does not always point us to the true maximum power point, but only in the region around the maximum power point, or as it's commonly called, the maximum power point region. Secondly, every time the system needs to respond to a change in illumination conditions, the maximum power point tracking algorithm needs to measure the open circuit voltage. How does the maximum power point tracking device measure the open circuit voltage of a solar module under operation? This is done by disconnecting the PV module from the load momentarily. Or in other words, the PV current is zero so as to measure the open circuit voltage. Although temporarily, this results in a loss in production of the PV power. This handicap only worsens if the measurement of VOC has to be made more frequently. A slight modification to this method can help in overcoming this apparent drawback. This involves the inclusion of a pilot PV cell that is highly matched with the rest of the PV cells that constitute the PV module. The idea here is that the pilot PV cell receives the same illumination as the rest of the PV module, and measurement of the pilot PV cell also gives an accurate representation of the PV module under consideration. Thus, while the PV cell provides for a good estimate of the module's open circuit voltage, the VMPP can be calculated as VMPP is equal to K times the open circuit voltage VOC. And the PV voltage can be adjusted accordingly without having to disconnect the PV module. Note that the inclusion of the PV cell merely avoids the losses due to module disconnection. This method would still suffer from the problem of depending on the K value for estimating the VMPP value. In this video we have discussed so far the indirect maximum power point tracking techniques. In the next video I will introduce you to some direct maximum power point tracking technologies. See you in the next video.